what we'll see here when it goes into the battle is the guy you're fighting against will still have a normal name, but you will have way too long of a name, and it will cause something called a buffer overflow. It's an old problem you'd have in like C-based languages where you don't have proper like safety of the memory, and it's going to execute part of the name that's too long, and then that's going to boot into files that are on the memory card. So now we're gaining total control of the GameCube. And you can see it's playing, I'm not touching the controller, and it's playing Kirby's Dream Land. And for extra fun effect, oh, sometimes this happens too. The cartridge bus on the...
So that's Travis for you. Travis mentions in the middle of this talk that he has a tool-assisted speedrun record for Pokemon Yellow, and it's like, you could miss it. He mentions it and then keeps moving. So many interesting things that he's done in this community. He's the administrator for the TASBot team and one of the official ambassadors for the TASVideos.com project. And he shows us so much that he's made in this space. So like there's a Pokemon catch rate calculator, there's a Pokemon DV calculator, and DVs are like the Pokemon equivalent of genes. So he explains all this. There's this other cool project, RGB scaler, that he made, and it's all about like how to actually represent the pixel information. They're not even really pixels, so you'll see about that. He shows us how lossless video recordings of some of this archival footage of games is actually less space than lossy, which is a real mind bender. Usually it's, I mean, in everything else, it's the other way around. So this is a really fun talk, got to be one of the most fun that we've ever had at MITS, and we really hope you enjoy. Let us know what you think.
Hi everyone, I'm Travis. You might now see me as TI Kevin83 online. There's a whole backstory on that I can give some time too. I'm a full stack developer at Gordon Food Services, and I'm an ambassador for TASVideos, the site where we archive records of speedruns of video games done with tools. That means running line by line in an emulator, and we'll talk more about that in a second. And then I'm also an administrator for TASBot. TASBot being a organization that does sort of charity fundraising by taking the TASVideos archives and playing them back live on real consoles in person for various demos, like you guys. So this is going to be a talk about various tools we've written in TypeScript, and actually, personally, myself, I've written a lot of them to help with Pokemon speedrunning and with tassing. So I talked a little bit about this. What is speedrunning? Speedrunning is trying to play through a video game as fast as possible, making some sort of arbitrary goal. So like for Pokemon, that's going to be like beating the Elite Four. Or in another game like Super Mario, it might be beating Bowser at the end of his Bowser's Castle, right? So, and then what is task verification? That's what TASBot does, where we take these to events. We have to play them, or not necessarily have to, but often have to play them live on original consoles, because sometimes people don't want Nintendo to know about emulators, and so we try to do that on real consoles the legitimate way in real events. So we take the task records people have done in emulators and inject them into real consoles. So halfway through the demo, we're going to see a task verification like that live, or maybe not halfway. I don't need. At some point, we're going to switch over and do that, and then I'm going to show some tools that we've written in TypeScript that are relevant to Pokemon speedrunning. So I'm a specialist in React Native and GitLab CI/CD at Gordon Food Service. I've shown some React patterns at JS World, and actually just this afternoon at 12:30 there was a talk of mine at React Summit earlier today. So I've done some speedruns myself. I have a task record in Yellow glitchless. Glitchless in Pokemon Yellow, it still has a lot of glitches, right? Those old games, they weren't written in C, they weren't written in a memory safe language, so they have tons of memory corruption glitches. So we just have like an arbitrary cutoff point called glitchless, which makes you play through most of the story and even still break some of the story. And then we have a no save corruption category, which again is another arbitrary set of glitches, because you can do this thing called save corruption, where you just turn off the game while it's saving, and you create a corrupted save that way, where you can have like, it's called bag underflow. You can go through to any of your items and change arbitrary memory and go straight to the Hall of Fame. So the no save corruption category gets you that item underflow, but it gets it through a way in the game that doesn't involve turning off the console in the middle of the saving operation. So I have the records in those no save corruption and the glitchless categories, and I'm officially an ambassador for TASVideos doing these showcases. What is speedrunning? These are often retro games that we're doing this timing, like trying to set a record in, but not necessarily retro games. So some people do speedruns of even brand new games. You'll see people having done speedruns of Tears of the Kingdom even that just came out. I think that around an hour and a half already, people have gotten to beating Tears of the Kingdom. So very fast-paced competition comes out for new games with, especially Nintendo games have a lot of speedrunning stuff. We try to add arbitrary completion goals to games that don't have like a set end game so that we can speedrun those too. Sometimes these runs require tools to help runners evaluate the quality of the run in real time, like stat calculators of Pokémon that we'll get to later. And what is tasking? We talked a bit about this, but tool-assisted speedruns play through these records frame by frame in an emulator. So instead of playing it like with a controller in real time, you have a keyboard and you have your computer and you look through line by line, frame by frame, and pick what inputs are gonna happen on every single frame of the game. The really important thing about that is that doing it in an emulator allows you to go back in time again. So you can do a bunch of inputs, and if they don't work exactly what you need to do, you can go back and re-record previous inputs to correct mistakes or ensure like a certain strategy is faster than a different strategy. It's exactly like a player piano. Have you ever seen a player piano play a piano automatically? It's doing the same thing, but in a video game emulator. And task records are tracked separately from RTA records on TASVideos.org instead of speedrun.com to keep the system separate and fair so we don't have people competing against real players with these tools. What is task verification then? I mentioned that we have control interfaces and methods to inject the inputs from the emulator back into a console programmatically. We convert input logs for a task from the format the emulator understands to a format that makes sense electrically for the controller. And we play the piano roll back on the real console instead of to the emulator it was written in. TASBot is notorious as a mascot for this process, and this proves that an emulator is accurate for all intents and purposes for speedrunning. So the only emulator we've really done that for is Game Boy emulation. Almost all other emulators have difficulties with this process. So we've done it for a lot of NES, a little bit of SNES, and some older stuff like Atari too. We've done this whole pipeline of proving that an emulator is 100% accurate. But as you get newer, it gets harder, especially for disk-based consoles like the GameCube here. It's very hard to get these to verify because the disk reading process is not perfectly the same every time. This also acts as an additional test suite to test ROMs for those emulators. So emulators have these things called test ROMs, where they verify if you play that ROM in the console, it shows a certain thing on the screen. And then the same thing essentially can happen using these task playbacks on the console, verifying that exactly what record you attempted to be beating is happening. Let's see, next here. Yes, Dimitri, let's switch over to the live thing if you need to change anything there. Okay, so what we have here is Pokemon Coliseum. What we're gonna try to do is we're gonna try to inject controller inputs from that piano roll log of a task into the Game Boy player. The Game Boy player at the base of the system is an entire Game Boy Advance. It has all the internals of a Game Boy Advance. Nintendo just figured out we could just strap it to the bottom of the GameCube, have a high-speed port that communicates memory directly between the two, and the GameCube can then have a disc in that plays the Game Boy Advance games. We don't want to use that disc though, because that disc doesn't have a way of injecting the arbitrary inputs. We need to make our own version of the Game Boy player disc. So we're going to do that by playing through Pokemon Coliseum for just a second to a point where we gain total control of the GameCube. So this memory card on the left here has a custom save of Pokemon Coliseum injected onto it from a Wii, where you can do homebrew very easily. And that custom save has way too long of a name for the character. The character input screen validates that it can only be so long, but the space in memory is much longer to save the name. So it's like 256 bits, but it's only expecting like 64 bits or something of space. So what we'll see here when it goes into the battle is the guy you're fighting against will still have a normal name, but you will have way too long of a name, and it will cause something called a buffer overflow. It's an old problem you'd have in like C-based languages where you don't have proper like safety of the memory, and it's going to execute part of the name that's too long, and then that's going to boot into files that are on the memory card. So now we're gaining total control of the GameCube. Now we're doing that again in order to play something on the Game Boy player. So I go into this GBI folder. I have a whole bunch of different tasks we've verified in here, but we're specifically going to play one back for Kirby's Dream Land. So when I click A into this, it's going to run Game Boy interface, that custom version of the Game Boy player's startup disk, but it's going to read off of the left memory card's SD card for those input logs like the piano roll. So we load that up. And you can see it's playing, I'm not touching the controller, and it's playing Kirby's Dream Land. And for extra fun effect, oh, sometimes this happens too. The cartridge bus on the Game Boy player is a little bit like dirty often. It's really difficult to get it to be happy about a game being plugged in. Yeah, very classic. There we go, okay. Should show it a little bit longer this time, hopefully. But you can see in the upper left, there's a controller like input viewer that Game Boy interface also has hacked in on top of the normal startup disk. So you can see it's holding the right button, and you can see any time it's doing any different inputs. And again, it's reading the log of which inputs to play on which frame here from the SD card. And it's timing, the way that the file format actually works is it's timing when to send the inputs based on the audio signal it's reading back from the Game Boy player. So every single cycle of the Game Boy on this part on the bottom, the Game Boy player, is counted by counting how many cycles of audio we're getting. And that's how we know when to send the inputs. Because otherwise, like if you tried to just count how much time has passed in the GameCube, that clock could drift from the clock that is at the bottom here. And we have some tasks like Pokemon Crystal where there's a real-time clock chip on the cartridge, which tracks like how much time is passing to get like day-night cycles. And for that, to verify a Pokemon Crystal game, we actually had to calculate the exact amount of drift that cart was experiencing, program a way in the emulator to emulate that wrongness of the chip oscillating, and then make the task against that exact emulation of the cartridge.
What would be the benefit, or like, why would you ship a game with the added expense of putting a clock in the card if the system already has its own clock?
The real thing there for Crystal was the cart was battery backed, so it could maintain tracking time outside of like when the Game Boy was off, and it could preserve the day-night cycles like when you turn the game back on without having to like set what time of day it is every time you load into the game.
So I have a question about specifically, like there's games with randomness in it, like Pokemon is a clear example of randomness.
Yes.
When it comes to that, are you like hijacking the randomness system or like pre-seeding it with something that you know what the outcome is going to be?
What you're essentially seeding with it is the fact that the system is deterministic. So Pokemon is a great example here because we've reverse engineered every line of Pokemon. We know exactly how it works. And what it does is there's a specific part of the Game Boy called the divider, which counts how long the system has been on. And because it's starting from 0, it's going to be the same every single time you play with the same inputs. So even RTA speedrunners actually take advantage of this, and they will hold certain button combinations during startup, play for like 5 seconds, get an encounter, and the encounter will be the same every single time because it's been the same amount of time the console's been on to the frame for that specific amount of time. This is just an extreme version of that where you're doing it for literally like minutes or tens of minutes at a time.
So have there been people who have turned it on and delay that seed to get a different seed so that they find a more optimal run with different outcomes?
Yes, what you have to do is like, there's like back in, back out things you can do. So you could like hold A to go into the start screen and then hold B to go back and do that. There's like, we call it windows of time that you have to hold those buttons where they will automatically apply at the first frame where the thing is reading inputs then. So there are certain strategies that do that sort of delaying. They will usually only do that if it's like during part of time that's not tracked in the speed run, right? So like in Pokemon Crystal Gen 2, there will be back in, back outs like that before the game starts, and then you hit start finally, and then you have a trainer ID that will always get you a Master Ball later in the game. Any other questions? Okay, so yeah, I'm not gonna let this play through. This will play for like 10, 20 minutes, so we don't need to see the whole task, even though it's very cool. It just proves the general concept of like this GameCube is now, effectively the GameCube is playing the Game Boy for us. We're really lucky to have this set up like this, because on the NES, we have to actually create custom controllers that talk to computers that send the inputs, instead of having this nice little self-contained unit that this is all official Nintendo hardware that is effectively playing the game itself. Including actually the SD card reader is official Nintendo hardware. They created it for, I think it was a feature of Animal Crossing. Okay, so now for the next part of the talk, there's a couple different tools we've written in TypeScript to help enable all of these things. Enable us to re-implement many less portable tools. Before like 2016, 2017, a lot of these tools were written in Java, which was decently portable enough you could run it on Linux or Mac or whatever you have. But they were often written like Java 7, and then there was like DPI scaling stuff that got added in Java 8, so they didn't run very well on modern systems, even though they were supposed to be super portable. So the first one is the Gen 1 catch rate calculator. The Gen 1 catch rate calculator accounts for a problem when usually trying to calculate the odds of catching a Pokemon. The actual observed rates are vastly different from the intended rates programmed by the developers. This is because of a rejection sample. So what essentially happens is, on the first side here, this is what happens the first time the Pokemon game checks the RNG. You were talking about how does it to do randomness. It's doing that thing where it's tracking how long the system has been on, and it's taking that number and then it's continually adding the state of how long the system has been on to it repeatedly, so that it'll keep rotating with that addition. And so the first time it checks a number is this time, and this second axis is the value of RDiv when it does that check, so the amount that was last added. The combination of those two things means that whether or not you catch the Pokemon is always the same value for the first roll, because it needs to do a random roll earlier to restrict the randomness for an Ultra Ball, a Pokeball, or a Great Ball. It's doing some stuff with the randomness to make it more beneficial to have the Ultra Ball. So because it's doing that thing right before it's doing the actual catch chance, those events become deterministically linked, and a bunch of the RNG states that would give you I catch the Pokemon don't give you I catch the Pokemon. They instead give you, they're not possible. They're just simply impossible to get to from the previous RNG state. So in order to actually calculate how wrong that is, we need to run through the full catch formula exactly as it was written in Game Boy Assembly in the browser for all of those different actual possible states of the RNG. We split this out into 16 web workers, one for each possible DV value of the HP. And we'll talk more about what the DVs mean in a few minutes for a different calculator. But the point is that the DVs are different like values of the HP stat. So it's another part of the things we have to calculate to make sure, I guess another way to explain it would be, when you have a wild Pokemon encounter, you don't know what its stats are until after you've caught it. So it might have like the perfect stat or the worst stat, and that actually then plays into how likely it is to catch the Pokemon through some really complicated parts of the formula. So we need to run the catch chance calculation for 16 different threads, which works out perfectly because we want to thread it and make it faster for your CPU. In the web worker, we actually run that RNG assembly simulation for the possible states. And this web worker allows the RNG simulations to be truly multi-threaded and have background operations. So normally, if you were to actually run through all 16 of those steps just in your main thread and not send it out to a worker, it would block CSS, and you couldn't even show a spinner to show that it was doing the calculation because it would block the rendering thread. So we send it out to the workers. We can actually show a little loading spinner, and then it goes back and shows you the results. And we do this on the client side instead of the server side because I don't want to have a server spitting out all this calculation 24/7 for people. The resulting average of all possible RNG results is compared to the book formula so that you can kind of see the difference. I'll just skip ahead there. So you can see here, the actual chance of catching a Chansey in the Safari zone is 4% when it's supposed to be 7%. just because a bunch of this input states are not possible to get to for where it thinks the RNG should run. Let's see a few more things about that. So creating worker threads, I'm gonna just apologize in advance. I wrote this code like 5 or 6 years ago, so it might be horrible and not how you're supposed to do this in like modern TypeScript. But we're just creating a promise, and then we're creating a worker. We're assigning a function to the on message for the worker, and then we post a message to the worker to say, here's all the data you need to run through all the RNG simulation. Then we resolve the worker threads by doing promise to all. A little hack here that uses the index of an array loop to generate 16 workers, and then just thens the results into one big calculation. Inside the actual worker thread, you can see we have one byte here for the RNG, and the second byte here, the initial state of that divider that's counting the time that the console has been on. We're looping through both of those things, so it's like 17 million different possible states it has to calculate. And then once it's done all that and added up all the actual successes and the intended rate, it posts that back to the full like main thread and closes the. You always want to do a close in a worker, otherwise it's going to stick out there doing nothing. And yeah, that Chansey example is particularly egregious because people always complain about it's so hard to catch Chansey in this part. Well, actually, it is harder than it's supposed to be. Another cool thing I wanted to mention this is something called AssemblyScript. The site currently doesn't use this because a couple other optimizations we did to the worker make it so that it would be like unnecessarily complex to maintain a little extra AssemblyScript library. But I thought it important to mention because people are doing like high performance stuff in these worker threads. This is an extra layer of optimization that you can do. AssemblyScript is a TypeScript-like language that enables simple transition to writing a WebAssembly module without having to learn C and then compile that within Scripting or something. So I tested it and proved it all out like in theory, but the simulation's not really slow enough now that it matters. So you could example, say, our Nidoran male. So it matters what version you're playing, red, blue, or yellow. They actually have like slightly different catch chances. It matters what ball type you're using. So if you're using the Pokeball, Great Ball, or Ultra Ball, if you look at the Great Ball, that tends to actually have the highest catch chances because the code is terrible. It's usually better than the Ultra Ball. And then you always get Nidoran at level 6. So we just check the rate there. The actual rate is only slightly different than the intended rate here. And this is because it's not very different for like high catch rate Pokemon. It really matters for something more like Mewtwo. So if I were to say how likely is it that I catch Mewtwo, this one, just by another sheer chance, it's actually way more likely to catch Mewtwo with a Great Ball than they were intending. Because a bunch of the states where the RNG would cause you not to then get the catch are just not existing.
Just a question. When you say they were intending, there's a line in the code somewhere. It's like assembly it's written in?
Yeah.
Okay, so there's a line in the assembly somewhere that says, for Mewtwo with the Great Ball, the catch rate is 1.04%. Is that it?
It doesn't say exactly like 1.04% because it's doing a bunch of formulas. Like it's more like the catch rate is like, I think the number's like 3, but then it has a whole bunch of ways that it says like your current HP versus the maximum HP of the Pokemon. If that's a bigger gap, then you have a higher chance of catching it. There's the statuses. So if you like put it to sleep, that also factors into creating a higher chance. But the way that formula works, it does all that and then it says, okay, compare a random number to that chance that I've like maybe it's like 4,000 out of 65,000 because it's like a 16-bit number or something. So when it does that comparison, the possible inputs for the random number are restricted because it's just called the random number like 5 seconds ago to check whether you have an Ultra Ball or a Pokeball or something. So it deterministically links the state of the randomness to the previous thing and makes a bunch of the actual calls impossible.
Okay, so, but in the process of developing these formulas and deciding on those kind of key values that feed the formulas, they're like playing the game, right?
Yep.
So wouldn't it be like, they may not have realized that the actual rate is really 1.74 and they sort of thought of it as being 1.04. But after all, they didn't even really think of it as being one. It's not like they, like you said, they didn't write in 1.04.
They were never even thinking of this number. They were thinking of a bunch of other math that they could try to hope, like, because they're programming in assembly, they really aren't seeing even numbers like 3. They're seeing them as something else. So.
Right, like hex values. So in a way, wouldn't it be fair to say that actually the values that are in the game in reality are exactly the values they intended, because they played the game and said, too much Mewtwo here, not enough Mewtwo there. Yeah. So then, like, it is the intended, it's just like,
it doesn't work the way that maybe they were expecting if they had done or they might not even been expecting it. They just, like, if you look at you could say like the book value. Like if Bulbapedia has a formula on their site for what the chance is, and you run through it, it's not going to be what the actual chance is.
But they didn't know the chance in the first place.
Yes.
Okay, got it. I got it, yeah.
But like you're building like, because your formula has to match the game.
Yeah.
So like Bulbapedia's wrong.
It's wrong, but to make it right would be way too complex.
Yeah, exactly. But like you're like in the tool assisted speedrun, you have to have like frame by frame perfect, right?
Yeah. This one isn't used so much for the tool assisted speedrun. It's used more for the like real time speedruns. It's used for a category called classic. Or there's another one called Ash%, where you play through the game as Ash in the anime, and you have to catch 25 Tauros because Ash catches 25 Tauros in the first season of the Pokemon anime. So you're like cosplaying as him essentially via the game. And this is when the problem came up. If you plug in Tauros in the species and check it for a Safari Ball at level 23, you can see, the rate is 6.6%. A speedrunner was doing this and saw this rate and was like, what? It's supposed to be this, not this. And so we did all the math the right way, and it turns out, it actually is 6.6%. Yeah, so that was the catch rate calculator. Let's show now the next thing. There's a second thing, the DV calculator. So Gen 1 Pokemon has DVs instead of IVs. You might know IVs if you know Pokemon. IVs are values 031 that kind of make how good a Pokemon is kind of random. So if you catch a Pokemon that has insane stats, it might actually not be as good as you think because it has all 0 IVs under the hood. Or you could have one that is like way worse, but under the hood it has 31 IVs, and so it actually functions really well for you. So Gen 1 has DVs instead of that system 0 to 15, which effectively map 2 times to the IVs. So if you have a 15 IV, or sorry, a 15 DV, it'd be effectively the same thing as having a 30 IV Pokemon in the newer generations. And the DVs are created by pulling for 2 random numbers. Half of each random number is used for each DV value. So you have attack, defense, speed, special. It calls one random number, it takes the left half of that and says that's the attack, right half's the defense, and then it does it again with speed and special. And then you also need an HP DV to make its HP variable. So it takes the last bit of each of the random number calls for attack, defense, speed, special, turns that into an HP DV, and then you have HP being not the same every time you play the game either. We have to give some background here. This is necessary due to a category split in 2016. We, in 2016, changed to time runs by real time, which is instead of the in-game clock. I mentioned earlier, we have the ways of like manipulating perfect Pokemon by playing for like 5 to 10 seconds. And in the post-2016 world where we time by real time, instead of the in-game clock, that's allowed. Before, because you were timing by the in-game clock, you weren't allowed to reset the console to be able to take advantage of that. So only now do you have those same Pokemon every time. And after 2016, when we changed those rules, we split in a special category that also more closely resembles the Japanese community's rule set for glitchless. And that one, then you need to like figure out the DVs in the middle of the run. You're not going to have the same DVs every single time, and you'll need different strategies on different fights based on the stats you have for those fights, based on what DV you got of the Nidoran. So you have to end up resetting the run repeatedly to find one with good enough DVs in the older categories. So we have this calculator here. The calculator shows what possible HP, attack, defense, speed, special stats that you have. And then you click on, I have a Nidoran with 13, 11, 12, 11, and it narrows it down to what your DVs end up being.
Sorry that it took so long to ask this question. What is a DV?
Yeah. So DV, determiner value, that's the thing that makes it random how good your Pokemon is. So like the stats are like, it could be like 100 attack, but if it has a really good DV, maybe now it has 110 attack. Or if it has a really bad DV, now it has 90 attack.
Okay, so it's like a gene or something.
Yeah,
that each...
it's like genes.
Got it. Okay. Sorry that I missed that. Okay.
Yeah, and like I said, if you're familiar with them as IVs from later gens, like trying to like breed a perfect IV Pokemon in Pokemon Go, it's the same thing. They're just half the newer numbers. This is a weird thing I did for this site, specifically using Pug templates. I wanted to shout this out. Pug templates are amazing. Instead of writing like brackets and all this stuff for HTML, you just say like element dot. What am I even doing here? I think the dots are like classes. Yeah. So you can say p.dv range. That's the dv range thing to apply the classes to that. And then I wrote this so long ago. It was in plain.js, but the idea is like as you're going through each of the DVs, you need to filter down to like compatible ones. So if we go back again here, 2 slides. If you say that you have 13 attack, that's going to restrict your attack DV to be like 11 to 15. And eventually you might restrict to being exactly 15. So now if you've restricted to being 15, you know that the attack stat is odd. If the attack stat is odd, that means the HP must have 8 more attack because it must have 8 or more attack DV because that odd bit then contributes to the HP DV. So as you're going through the calculator, it's actually filtering out a bunch of the other impossibilities in the HP. Now, this is the really fun thing I wanted to talk about here, rgbscaler.com. I've been talking about this at JS World and React Summit. RGB Scaler takes care of a bunch of problems in retro video archival. So the 5 of them are chroma subsampling. Really, really simple thing for chroma subsampling is color reduction. In really old footage, like Game Boy or NES footage, they just have full color. They have as much color as they have brightness information. Sometime, like when they did the color TV transition from doing like black and white to color TV, some really, really famous person who has caused much problems for the world said, let's make it backwards compatible so that color TV can be played on older black and white TVs. So instead of sending the signal to the TV as red, green, and blue, they send it as brightness and difference from blue and difference from green or something, which is like mathematically you can use to compute red, green, and blue. So because of this, every video in like actual like computers and monitors since then has this thing called chroma subsampling because some other guy said, hey, if those signals are separate, we can make them have less data on them and then use less data over all of our wires. So games weren't chroma subsampled. They were just like, oh, we can go straight to the monitor. We don't need to worry about data efficiency going just from an NES to a CRT. So they don't have that chroma subsampling step. But then if you try to record a video at the native resolution of an NES game, it'll have too little color because of that. They also have stretched aspect ratios. So really simple explanation of this. NES is kind of close to a square, its aspect ratio when it's output, but on a CRT, everything becomes 4:3. If it's 256 by 240, now it's 320 by 240, but it's not actually 320 by 240, it's still 256 by 240, just rectangular. It just paints a little bit longer on the phosphors on the CRT. But you can't do that on a modern screen because it has a fixed number of pixels now. So now you have to show it at 320 by 240, and that causes artifacts too. So what you actually have to do is save the footage at 256 by 240 and only do the stretching at the last step where you're showing it to the person on their monitor, which of course you can't do on YouTube. YouTube just bakes the aspect ratios in, so it makes it all blurry. We also have to upscale for modern displays. Like the most color accurate displays like an LG C2 or your other like QD OLED displays are going to be 4K, huge batch of displays. You have to have some way of taking the tiny pixels and making them tons of pixels. The algorithm that browsers use to do this is called bilinear. And it looks really good for film and horrible for video games. So if you're doing upscaling on a video element, it'll butcher your pixel art. And what we end up having to do with RGB Scaler, the reason this site was built was specifically for this part of the 5 problems, which is to force using a thing called a sharp bilinear algorithm. And we'll get to that in a second because that we'll need to get in more detail of what we're doing. Two other possible problems are lossy compression versus lossless. YouTube, most video hosts host lossy archives because if you take, again, like film, it compresses very, very effectively. If you do lossy compression, but not very well for lossless. It's gonna be massive if you try to make a lossless version of a film video, but retro video games don't really work well with like lossy encoding. They just create a bunch of artifacts, but they are really, really efficient to compress because you have these giant blocks of exactly identical color. So we really would prefer to use lossless compression, but in the most commonly supported video codec called H.264, the only support for lossless mode of that, with also not having the color problem, is Chrome on the desktop. Firefox, Edge, like everything else, and also like Android and iOS on mobile do not support lossless playback of H.264. So we have to use other codecs specific to different devices. And then the last important thing to mention for this is sometimes the art was designed for how bad CRTs and the cables to send things to them were. So you'll have things like phosphor decay and composite signaling, which cause blending between pixels. And what you could do with that is you could use something called dithering, which looks like a checkerboard pattern. So you'd have like a checker of blue, blue, white, white, and now you have this half blue where you have the checkerboard that the console can't actually create because it only has 256 colors or something. Now you have 65,000 colors because you can create half colors by doing the checkerboard and then having the CRT butcher your footage. So sometimes you actually have intentional degradation wanted to be able to see it the way that the artist designed the footage. This is a demonstration of the area effect problem. So this middle one is what bilinear does to retro game footage. The left one is what nearest neighbor or point does, and I like to compare this to the Mercator projection because it creates you perfect latitude and longitude lines. You have perfect, sharp lines of pixels, but as Link moves left or right, it's going to wobble. Its shield is going to be bigger or a smaller width. So in the upper one, Link's shield is 5 pixels wide. The bottom one, Link's shield is 4 pixels wide because if just for the sake of example, you wanted to upscale nearest neighbor 4.5 times, it's gonna go 4 on one line and then 5 on the next to average it all out to being 4.5. What we want to do over here is the area effect, where we take the bilinear only on those edge artifacts where it's saying, I'm going 4.5 times. So it'll do 4 pixels of the exact original color upscaling, and then on the 5th, it'll say, oh, I can't do that. I have to go an interpolation just for that one line. This is what Atari Dragster looks like if you do all 5 of those things wrong that I mentioned earlier. And this is what it looks like if you do all of them right. Now, it's not going to actually be as dramatic showing you over the projector and everything. It's gonna still be a little bit blurrier, but you should kind of be able to see, especially when it's blown up a ton on the right side, that there's a bunch of artifacts, and then when you go to the right side, none of that is actually in the original footage. And then this is what it looks like if you simulate a CRT on top of it to try to like create some of the effects they might have intended from the problems that CRTs have. So if you get out your phone and look at this QR code, hopefully we should be able to see some footage of an old NES game. The controls are different from a normal video player because when you re-implement a WebGL video, it doesn't give you the controls from the video you're copying from. You have to have all custom controls. So you'll need to like click play in a little separate button. I have BrowserStack access as like part of a sponsorship to be able to test this on individual devices. So hopefully we can go back and test more of it. But you got it working, sweet. Are you using an Android phone or an iPhone? I got Pixel 7. Pixel 7, okay. So it does tend to have better success with Android than iPhone, but I have a point in here. I did do some testing on iPhone to get a little bit more working there too. So on the Android side, this has to use the AV1 video codec. They just came out with this recently, and it supports 4:4 and lossless footage on like mobile phones, which is quite useful. And it's compatible also with like Firefox, Chrome, Android, a whole bunch of stuff. And let's see. Oh, yes, the H.265 video codec is what we try to do for Safari, but it's really, really difficult to get it to work right because they will try to force over to a different type. So if you say like, hey, I have the video, it's an MP4 codec, HVC1, which is the same thing as H.265, it will say, oh, I can't actually see that sometimes. It's very picky. Especially if you, what I really wanted to do is have a fallback to H.264 because that's more broadly compatible, but you can't give it that because iOS doesn't respect the order of the fallbacks. You're supposed to say like, do this one, then this one, then this one, and it will say, oh, I see you have H.264, I want that one, and break spec. So how to send video to WebGL texture. MDN has a whole tutorial on this, but I've adjusted it for React. What we're doing is we're sending uniforms to a shader program. So for things like the slot mask and scan lines on CRTs, those are just like the sort of effects that the CRT has that make things look worse. It sends values of that to uniforms. And then we have like use effect hooks to handle resizing. So if your canvas height or width changes, or you change the like output display aspect ratio you want, you can just resize whenever that happens. How does the WebGL texture update for new frames of video? So there's a render loop, and the render loop says set animation frame, which this is a use ref hook, the set animation frame, and it's setting the value that we get back from running request animation frame on the render loop. So request animation frame, it actually like pulls your device's refresh rate. So we're rendering something as close to what you can do on the frame rate of your device, as well as to as close as you can do on the screen size. We use that as a way of being able to cancel the animation frame, because if we, for instance, pause the video, you want to pause the WebGL canvas associated with the video. So we just cancel the animation frame using that use ref hook value. These are the essentials of the shader I was talking about. So we have these slot mask and scan lines, and this math lets you say, hey, instead of painting all the lines like this of an interlaced footage, pretend that they're painting the same lines repeatedly, because that's what the NES would do. All CRTs operate as interlaced for their 480 lines, but the NES only outputs 240 lines. So what it would do is, instead of painting these and then painting the alternating ones, it would say, give me field 1, and then give me field 1. It wouldn't give you field 2 ever. It would just say, give me field 1, give me field 1, over and over again. So you would create like these empty spaces in the CRT. That's called scan lines. And the slot mask is doing something similar, but it's doing it with the subpixels. So like red, green, and blue. Instead of blowing up, treating it like as the actual color, it's treating the pixel as the 3 subpixels when it's blowing it up. So it's blowing up like little bits of red, green, and blue to the screen. Which that has the bad effect of making it look a lot darker, but it looks a little bit more accurate to CRD. Getting syntax highlighting for shader code. This is super, super helpful. If you're writing WebGL shader code, usually you have to write it into like a template string because it's going to be in a JavaScript file. But if you use a rollup plugin string, you can write them in vertex and fragment shader files, and then it will pick up, oh, I need to use the syntax highlighting there, and bundle it into your JavaScript for you at build time. And like I said, because we were on a WebGL canvas instead of the video, we have to hide the original video so we don't have 2 videos playing at once. We have to write all custom controls. So you have things like a React button that has a little handle, play, pause, click, and then it does that like request animation frame or cancel render loop. Another really important thing is working with DPI scaling. So you guys might know about this as website developers. There's this really important thing called device pixel ratio. And that is the ratio between CSS pixels in your browser and the actual pixels that your phone has on the display. If you were to not account for this, it would give you an artifact the size of the CSS pixel and not an artifact the size of the actual pixels that your phone has. So we have a different setting of the canvas width and the canvas style width to maintain the sharpest possible footage. And some compression efficiency takeaways. If we take that like dragster picture I showed, the lossless footage of that is about 120 kilobits per second, which is about, 500 times smaller than 4K footage usually is. And the only other way you could get that sort of quality, like uploading to YouTube, is first taking the video footage, upscaling all the way to 4K or 8K, and then having the user watch it on YouTube in 8K on their smaller resolution device. which YouTube often now says, hey, we want to make you a paywall for 4K. I think I've heard stuff about that too. So really important to have technology to do that in a static site. And then for something even newer like Super Mario 64, we can get 5 or 10 kilobits or 5 or 10 megabits per second for that footage, which is still smaller than 4K footage, which is lossy. So we're doing lossless at these 5 to 10 megabit rates for N64 footage. Yeah, a whole bunch of other garbage about compression efficiency, which, yeah, it's way smaller than YouTube, and it looks sharper.
I guess maybe going back to the beginning when you were talking about running things on real hardware, how do you test this? Do you have like a lab with different devices and have like some sort of automated CI that runs them?
We started doing that actually. So we have what I didn't do this in CI yet, because to do it in CI would mean you'd have to host ROMs somewhere for the games to then be able to run all of the stuff back against the game. So one person who's doing Sameboy does have that all set up, and they have like a local runner on their machine for the CI that has access to all the ROMs. So they're not doing any improper ROM distribution. It's all clean room still. But for that site, I'm just doing like manual runs of it every once in a while against the emulator to then test that it's still working the way we verified that it did on the hardware.
Could you do like any like ipfs stuff with like hosting ROMs?
ipfs?
Yeah, it's like it's a blockchain thing. It's like you can it's like a URL, but it's ipfs. So
yeah, I could look into it. Probably we would just avoid doing it just to be extra safe. Like these TASVideos sites, like we used to use BitTorrent, and we even stopped like hosting our stuff on there just because we don't want to be associated with it just for extra safety.
So like, what's the big picture going forward? I think like the story arc that I heard is that like for taking a look at these old sources, there's these, you're coming up with these techniques for like archiving this footage or being able to capture this footage. Like where would you like this to like, is there an end game here? Is there like an end state that we're kind of like, that you, I don't do any of this stuff. Is there an end state that you're working towards? And if so, like how close do you think you are?
Yeah, what I would really like is in terms of an end state, because I think it's going to be impractical in a certain sense to get everyone recording their footage to this level of quality. You have to mod consoles with HDMI often to be able to get them to the same sort of clean, like no noise footage that would give you that perfect compression where all the color is perfectly identical. So it's kind of impractical in a sense of getting everybody to be able to record to this level of quality to then even be able to be worth it showing in RGBscaler.com. The real value is in like having validated this pipeline, we can show the benefits of like why you would want to use a sharp bilinear scaler for retro game footage. So one of the things I forgot to mention earlier in the talk is the reason this whole thing is necessary is because of another thing with breaking spec. All of the browsers right now have this thing called image rendering.pixelated in CSS, and they all implement it wrong. It's supposed to be the sharp bilinear thing I showed. It actually says that in the HTML spec, or the CSS spec, that you should have a partially sharp filter for retro footage if you use pixelated. And there's a second setting that you can use for like crisp edges, and that one's supposed to be nearest neighbor, but everyone has just implemented nearest neighbor on pixelated, and also only done that for images often. If you apply it to video, they haven't even implemented it operating on the video for most browsers, except Firefox. Firefox on the desktop, you can actually hack in this technique with like a grease monkey script to any video, like YouTube even. You could like go in and say, hey, make it image rendering pixelated, and now your YouTube has the proper like area upscaling, but it's still not area, it's nearest neighbor, so it still has like wrong shapes of things. So really the point of all this is to like show, hey, browsers, please implement this thing to spec so we don't have to do all of this garbage.
All right, thank you.
I got into doing tasking eventually because doing the real-time speedruns, I got up to like 3rd or 4th on the leaderboards and my hands just hurt horribly. Because what you're doing is you're like holding a controller like against your leg to try to balance it and then doing this for like 3 hours at a time, because you need to be mashing at like 15 hertz to like match the text speed of the game. So yeah, it was not healthy. So I stopped doing that. And I did it in tasks where you can do it at your own speed and look at it line by line, which I think the first time I did a Pokemon Yellow glitchless task, it took like 9 months because it's 360,000 frames that you're having to do line by line.
So what was your fastest run where you were using Yellow manually?
156.20 or something like that.
So 2 hours of mashing?
Yeah, you don't do it the whole time. Once you get really good, you can kind of like do it as the text box is getting close to the end, and then just do it for a few seconds. But
Is there any like copying somebody's
yes,
tweaking it?
that's a really important question. So all of the runs on TASVideos.org are a Creative Commons license. So once you publish something on the site, it is completely open for other people to use, except that it's an attribution license. So you have to say, I copied this from this person. Well, the really important thing of the TASVideos site is we judge all incoming runs. So if somebody doesn't do that attribution properly, we figure it out pretty quickly and then say, hey, you did something shady because you're telling us that this is yours and we have a copy of it that is virtually identical. People will do that all the time for Super Mario Bros. Runs. It's very common for like NES Super Mario Bros. People are like, hey, look, I did the task and I got the record. And it's like, well, we have the record already.